Tom, one of the things that a lot of scientists are sharing with us is sort of lessons learned about dealing with the media, dealing with the public, and how to communicate their science. And some of the things that hold them back, some of the things that help them do the job a little bit better. You have any observations?
I do. But I found that with all the people that called me, and I had a lot of people from the Associated Press, and just as everyone was getting, and it was really interesting to see how uninformed they were about sort of the general methods of science and the way we sort of sit back and try to approach the problem in a logical way, sort of hypothesis-driven based on what we know. No one wants to hear that material. It's typically very boring. But without the scientific method, it just turns into a bit of a bedlam. You can have lots of people out there, and it can look really good that there are lots of people in different boats. And if there's no consensus as to how to go about sampling and some thought process in that, it'll lead to nothing, and you can have lots and lots of data that are unusable the way they were sampled with no planning. So I think it was the typical media rush of wanting everything simplified and distilled down. And again, it was a tough thing for me to learn to do, to try to distill as much as I could and not use technical terms.
There's the process of doing science, and then there's science itself. And science itself is an interesting subject because it's actually a philosophical discussion, and that's why scientists typically have PhDs. They're doctors of philosophy. The process of science, there are no specific written rules. It's an ethos that we have to play by, a set of rules that are accepted by a community. And because it's all accepted by a community of people that call themselves scientists, we think of the process of science as being self-correcting. And scientists who really are scientists, who appreciate the process of science, appreciate the long-term self-correcting of this. And that's because to make advancements within science, you always have to fall back on the community, your community of peers. And there are a variety of ways that we've embedded within this self-correction. And we typically think of it as peer review. Peer review comes at many stages. We have our colleagues reviewing our questions, our work, our product constantly. And if something is not at a community standard, a peer standard, then it gets corrected. So with the oil spill, and you throw the oil spill in the middle of this scientific process, the corrections need time. And so people who are looking at the oil spill going on 3 months of staring at a computer screen or a TV and watching this oil billow out and wondering why the scientists aren't doing something about it. Well, the scientists are doing something about it. It's now become part of their scientific fabric here, and they're asking questions, and they're doing things. The scientists are doing their best to speed the process up, but you can't overspeed the process because the system will break if you do.
As a scientist, what makes a scientist? My point of view is that a scientist follows the scientific method. The scientific method begins with some observations. And based on those initial observations, we put together our hypothesis, or an educated guess on how a natural system functions. From that hypothesis, that by absolutely no stretch of anyone's imagination is that what we consider to be fact. This is just what really an organization strategy to help to guide our research. We take that hypothesis, we formulate some tests to try to get a more rigorous understanding of that. Those tests can be completely contrary to our hypothesis, and we can completely throw that out and start over. Or it can show just some slight flaws in our hypothesis for necessary revisions. But it's that iterative process of hypothesizing and testing that we have to go back and forth many, many times over a much longer time period than we have for the spill that ultimately leads to our theory or a very well substantiated explanation of things. As scientists, sometimes we fail and we relax that process and we just say, well, you know what, let's just go out and measure what we can measure with our fancy instrumentation and see what we see. And I think that's where, in times, we as scientists can fail because we don't really have that focus, that drive, and because of that, then we can't communicate that very well to the public. However, we also need to recognize the fact that we need to communicate what the scientific process is. For those of us that are following that, which is most of us and most of the time, we have to really communicate that these hypotheses are really our best guess based on the knowledge and the data at hand. And debating those results, getting new results that add then new insight to possibly revise that hypothesis is not a bad thing. Proving somebody's hypothesis wrong is fantastic. Proving our own hypotheses wrong is fantastic. Because what it does is at the end of the day, you've advanced knowledge in a way that at the beginning of the day, we didn't have. When we went out in the spill, we thought some of this methane would go to the atmosphere. None of it did. We proved our hypothesis wrong. We thought methane would reside in the Gulf waters for years to come. It resided in the Gulf waters for a few months. We proved our hypothesis wrong. At the end of the day, the knowledge of how the planet functioned both in this spill as well as globally was advanced. And communicating that process, both on how we can test and change our best explanation of things as new data becomes available, is something that we need to do as scientists, to communicate that to the public.
Well, I think the frustrating part of this whole experience for me is that all we had the opportunity to do was react. And even though we knew that this was going to happen eventually, there were absolutely no plans on the ground to react to an oil spill in the near coastal waters. And as a result, the public became incensed relatively rapidly, and they're working on a 24-hour news cycle, and science takes a whole lot longer to conduct from the point of observations to hypothesis to testing and then testing again. And there was such a disconnect with that it became an is-not-is-so story in very, very rapid fashion. And then the rest of it was that the public media was not vetting the people that they were putting on the cameras, and people were speaking as though they were professionally trained scientists when in fact they weren't. And so it became conspiracy theory in a very short period of time, not science theory.
So that scientific process of hypothesizing, testing, getting new data, and revising is also something that takes time. And unfortunately, in events like this, where we do have a disaster scene, where we want answers now to both help responders and residents deal with this spill and understand what life might be like, it's not uncommon for us to put out our data that's initial, to put out our hypotheses that are initial, and there's no problem with that as long as it comes with the caveat that a well-substantiated theory takes a very long period of time. Science definitely takes time.
Was very difficult for us to deal with was the public wanted to know what we thought or what we knew, and we didn't know very much. We thought a lot, but it became a very difficult opportunity for scientists, to examine how we were supposed to communicate for the public, and there was a lot of dissension in the community. The people said, well, we have an obligation to tell them what we know. But the problem, of course, was that most of the media, even the good mainstream media, cherry pick what they want to hear from the scientists. And we've talked about this a lot. It's very difficult to deal with that. Occasionally you'll find the reporter that will add a caveat that justifies some theme in the story, but I promise you the editor never puts that in the title. And that is a lot of the problem, I think, ultimately in this.
I mean, one of the problems we had with the assessments was that it was very difficult to get access to oil and dispersant samples from the Deepwater Horizon site, and that was because the attorneys were already involved in this. And so it delayed a lot of the evaluations that the scientists were doing, and they had to shift them from doing it in the field to doing it in the lab. And the results are as complex as a natural food web is. And if you're looking at things that are at the small level, microbial organisms, plankton, that sort of thing, there appear to have been effects. The composition of the communities at those trophic levels did change some. Whether or not they're still changed or not is not known, whereas composition of fishes and birds didn't necessarily change that much. There was certainly mortality in all those cases, but it looks like they'd be able to rebound. Now, that's the immediate effects. Now, over the long term, if the plankton turn out to be really damaged in some way or dramatically altered in some way, over time, it's reasonable to predict that there will be cascading effects that would affect juvenile snapper or small sharks or plants or what have you. And it just takes time to properly conduct scientific evaluations, and you have to recognize there are direct effects and that there are indirect effects, and the indirect effects are harder to detect.
I think lots of people sort of had an ugly view of the scientists as well in terms of when there are disagreements, and the public's not aware of the fact that that's what we do all the time. It's not that we're disorganized and we don't know what we're doing and we have all of this infighting going on, and we'll never get to the bottom of things because of all this infighting. That's sort of the normal process of science. We really don't deal with facts. We deal with tested hypotheses, which means you can always keep changing information. It's never always the same answer. And so it's sort of an ongoing process, and that's a really difficult thing for people because people want the black and white side of it. They don't want the gray.
So there was an interesting problem with the oil spill, and the agencies, the scientists themselves, the funding agencies and the agencies that were doing the management and regulation, the NOAAs, the White House, Congress, and everybody was doing their best to fit within the existing architecture how to deal with a major catastrophe like this. I mean, there are laws. We had guidelines for dealing with this, but the scientists themselves couldn't find a place to fit in the scientific process. Because we want to ask questions and better learn from the what's going on to try to understand the world around us. So people like me who are using this as a vehicle to understand the world around us were sort of peripherally located around the response and recovery and now restoration activities that are going on around this oil spill. So for me, science had a place at the table, but it took a sort of a back seat to all the other activity that was going on. Now it's a little bit different. The oil spill has stopped, the well's plugged. We're backing out and trying to understand what really happened during that 6-month or so window of time, and into the future, what the long-term impacts might be. Now we're actually asking comfortable scientific questions, and so the scientists now can come out from the background and emerge into the foreground of this whole process, and actually play a much larger role than they had been playing in the previous year or so that we've been dealing with this.